And, oops, wait. Where are we now? It's time to take our break. Yep, it is. No, I'm determined to keep to my word, so we'll take a break. So I showed you the graph of a curve of known objects, and they are radiocarbon dating, and they line up in a straight line going back to 6,000 years. So something less than 6,000 years, which has carbon in it, can pretty much be dated. That's an amazingly close straight line.
I'd be interested in knowing. Can you read what those are?
Yeah, well, tree rings, Dead Sea Scrolls, Ptolemaic coffin, Tiamat, I don't know what that is, Redwood, Seti, Sensuret III, which I believe is an Egyptian, Snowfru, Djoser, and D. Djoser and D. Jet. I have no clue what those are.
How do they know how old the Earth is? I mean, where do you dig for that?
That's class 4. Let's finish this one up. Okay. Volcano in Hawaii goes, throws out some lava. The lava is coming from the mantle, which, as we found, is fairly well mixed. So if lava comes up, it's going to have it's coming from the same source. That source is always replenished. It's kind of like the carbon-14, so that when lava comes up and solidifies, it stays in that state unless something changes it. And there are many places where lava has flowed and then flowed and then flowed and then flowed over thousands, millions of years even. And if you look in those, there's a fascinating change from potassium, which is abbreviated P and K. How do you spell potassium?
Two S's.
Yeah.
Okay. Potassium, and I don't remember what the isotope is, but it degrades into argon, which is an inert gas throwing off something. So, I go out just after a lava flow. I go to the places where it's cooled off enough that I can walk. I smack off a piece of the lava, take it back to my mass spectrometer, and what do I find? There's no argon. Why? Argon's a gas. It was in something very hot. It boiled away. Argon doesn't stick around in that first lava flow. And since it's inert, since it's one of the gases like xenon and so on, it isn't going to react with anything in the rock to stay there unless it stays there in a not the surface. It can escape from the surface, but it can't escape from the inside. Well, after time goes on, the potassium turns to argon, and now we're 4 layers down. We're back about, I can't think, 100,000 years. And now you can add measurable argon. And you have a measurement of the amount of potassium as well. The ratio of those two can be used to date lava flows and anything caught between them. Lava flow, long time ago, covered with dirt. People farm, they do whatever, they put up their houses. Catastrophe, Pompeii, lava flow, and all that stuff, the people, the wood of the houses, the trees, and so on, is now encased, if it didn't burn up completely, between layers. And I can date the top layer, and I can date the bottom layer, and get a good average estimate for what was in between. There also, I really like this one because it's something you can kind of wrap your head around to say, okay, it starts out with no argon at all because it's boiled off. And the decay forms argon in the rock. And that somehow, that's clean. It's very elegant from my point of view. The next one that's used, the next one that's commonly used is uranium, which turns into lead. Now, why is this one important? It's because uranium has a half-life of millions of years. So, and it depends on which isotope you're talking about, 235, 238, 239, and so on. But the one they measure takes a very long time to degrade. And you can do the same thing. You can, find a layer that has uranium and no lead. And then as you go deeper and deeper and deeper, you find that there's more lead and less uranium. And again, the ratios and other measurements can be used to date something that's millions of years old. As long as it has a little uranium, and it turns out uranium per se is all over the place. It's just not the toxic variety. Any questions? No. Okay. Does anybody object to us trying to start class 4 today? Or shall we have more discussion of dating things? Let me get some photocopies.
Okay.
All right. The class has decided that they want to begin with class 4. Okay, class 4 is about the earth sciences and geology. We'll get through the first portions. If you think about it, how do we know things about the world was something I asked you at the beginning of the course. And pass these around.
Why are you doing this?
I forgot to do that during the break. And 2,500 years ago, Greek Pythagoras, gave you that equation: hypotenuse squared is equal to the sum of the two lengths squared in a right-angled triangle. Well, it turns out 2,300 years ago, Eratosthenes calculated the Earth's circumference to about 46,000 miles. Now, you know that is way off of what we know today, which is approximately 25,000 miles circumference, right? But it's really close. It's only off by a factor of 2, and he did this by hearing from a friend that there was a well 25 stadies, let's call them miles, 25 miles south, and in the midsummer day, the light from the sun went straight down that well. It didn't cast any shadows on the walls, and he thought that was fascinating. So Eratosthenes went to his well, midsummer day. He looked, and the rays were coming at an angle. They formed a shadow in his well. He measured it. The difference was 7.5 degrees, I believe. And and so he was able to make the calculation, which we'll actually do as one of our experiments next time. William Smith was an English surveyor who was also interested in mines and minerals. And what he noticed was that wherever he went in England, there were always the same layers. And he thought that was rather odd. So you've got a layer of rock, of substance, let's say that's chalk, You've got another layer of glacial till. And this is, let's make this sandy. So you've got glacial till, and on top of that, you've got magma from a volcano eruption or whatever. But he found that when he went into the mines and when he did his surveying, the places where they had cut a road straight through a hill and chopped the hill in half, he could find the same layers. Then he looked closer and he noticed that, well, this is really weird. I find sand dollars in this layer. Remember our famous sand dollars? But I don't find them anywhere else in this stratigraphy of layers. But let's pretend this isn't magma. Let's pretend that it's something else. And over here, you find fish bones. But you never found fish bones down in the layer that had the sand dollars. And in here, you found worms, nematodes, some of which were segmented like an earthworm. My beautiful artwork. But he found that the layers not only were consistent all the way across England, no matter where he went, it seemed, but the fossils, the objects, were only found in certain layers. So he came up with two hypotheses, or two principles. One is the principle of superposition, which says sedimentary layers, I'll come back to that, are deposited in sequence, with the oldest on the bottom and the youngest on the top. Well, if you think about it, unless it's been turned over by an earthquake or something, there's going to be a top and a bottom. And the principle of faunal succession, he says different fossil animals are found in different layers, and the fossils change with time. So what he's saying there is, this is time. This is the oldest, and this is the newest in terms of layers. In terms of layers. There. This was big. This was really big. He got a lot of criticism for this. Now, however, people who were open-minded and just looking at the evidence can go and see that this is true. And that picture that I showed you where the fat sea urchin slowly flattens and then gets into a fat sand dollar and then gets into what we see today. Well, these were also in layers. And what his principles mean is this is older than that, this is older than that, and this is older than that. And because I can see a change as I go, he makes the logical conclusion that animals change. The fossils change over time. And that was a phenomenal revolution in terms of the natural philosophers at the time who were doing science. That was a really, really big deal. Question?
That was before Darwin even.
1700, yes. Yes. He that information was, I can't remember if it was part of what he said, but he should have.
Are you saying that the sand dollar with a hard outside turned into a soft fish?
No.
Oh.
No.
So where did everybody come from?
Well, the thing is, everybody branches off really fast. That when a body plan is comes to fore. But I'll get to that next time with the fossils.